Hi friends, welcome back to the session. In the last session, I think we started armature reaction topic, and because of armature reaction, we are having a demagnetizing effect and a cross magnetizing effect. And I told you to reduce cross magnetizing effect, so I can say to improve commutation, to reduce spark with the brushes, we are using shifting of brushes along MNA in olden days. Okay, I think nowadays we are using interpoles, but in this session we'll be discussing shifting of brushes along MNA. Let us see. Yeah. So shifting of brushes along MNA to reduce CME. Okay. So please, I request all of you, before watching this video, please try to watch previous videos so that you'll be having some clarity. Okay. So how you have to reduce the cross magnetizing effect, or because of cross magnetizing effect only, we're having a poor commutation, we're having delayed commutation, we're having under commutation, we're having sparking of the brushes. So indirectly, if you are reducing cross magnetizing effect means so indirectly I can say that we can reduce sparking of the brushes, we can improve commutation. So all those things can be possible by shifting brushes along MNA. That is what I can say. In olden days we were using this method. So let us discuss this method, and I'll tell you what are the problems in this method. And now why nowadays we are using interpoles winding interpoles. So that using interpoles, how can you reduce CME? That we'll see in coming sessions. Okay. Let us see shifting brushes along MNA to reduce CME. Okay. I think in the last class I had already taken, I assumed main poles. Let me take this one as North Pole, South Pole, and here this is nothing but Q axis. I can say, Q axis. So what is the other name for quadrature axis? So please, so interpolar axis, quadrature axis, Q axis, geometric neutral axis, axis of commutation, axis of symmetry, and I can say this one as a brush axis also. Okay. So here the problem is, try to let me show you this figure. So here initially I told you in this, whatever the conductors which are placed under North Pole, in those conductors direction of EMF I got cross. If you want, I'll show you that. So see, try to see that first figure. Yeah, see, under North Pole, whatever the conductors are there, so in those conductors, because of the interaction, so I assume direction of TPM in clockwise direction. So for direction of TPM, for clockwise direction of TPM, I got cross in the conductors which are under North Pole, and I got dot in the conductors which are under South Pole. Okay. So what I'm doing now, so initially under no load condition, GNA and MNA are they are coincident with each other. But under load condition, because of armature current, because of armature flux, your MNA will be here. Okay, MNA shifts from GNA by an angle of theta. This theta depending on the load, or I can say depending on the load current. So now initially brushes are here. So what I'm saying, if you want to, if you are, because of this cross magnetizing effect, we'll be having the sparking at the brushes. Let us see how can you reduce the cross magnetizing effect. So for that, what I'm doing here, in olden days, what they were doing, where they were shifting brushes along MA. That means initially brush is here, no, this white color. So let me place this brush. Let me shift brushes from along. I can say let me shift brushes along MNA wherever MNA is there. So there I'm just placing brushes like this. Okay. So this figure only I just drawn here. Yes, here is MNA, and this is what I can say shifting a brush along MNA. And I told you, if you see, if you take brushes in the left hand side, whatever the conductors which are under North Pole, I told the direction of EMF cross. So please let me show once again. Yeah. So if you take brushes here, so for the brushes, if you take left hand side, in our example, so in those conductors I am getting the direction of EMF cross. So under right hand side of your Q axis, I got a dot here in our example. I'm saying in our example. So please guys, so after shifting brush along MNA, so to this along, if you take these brushes to the left hand side of your brushes, I can say this conductors, let me take here a cross, and to the right hand side of brushes, let me take a dot here. So I think this diagram is, I think it is easily understood for you. Okay. So let us proceed now. So guys, now what I'm saying is, so please, if you shift brush along MNA, so now tell me direction of this cross and dot means what direction of armature current, So now tell me by using right hand thumb rule for this direction of armature current cross, so what might be the direction of your armature flux? Very simple. Apply right hand thumb rule. Your thumb indicates direction of armature current. Rapid fingers indicates direction of armature flux. So please, your thumb should be into the board here because I'm getting cross here. So let me use laser pointer so that you'll be having some clarity. Yes. Here, let me show thumb into the board. This cross means direction of armature current entering into the board. No, entering into the board means you have to show thumb into the board. If you show thumb into the board, remaining rapid fingers shows direction of your armature flux. That is what I can say clockwise direction. So let me show direction of armature flux. Armature flux, yes, like this. This becomes direction of your armature flux. Is it okay? Direction of armature flux I can say, okay. And similarly here, dot is the direction of armature current is dot. That means out of the board. Your thumb should be out of the laptop or it's out of the board. So now rapid fingers, direction of armature flux becomes the anti-clockwise direction. It will be like this. I think it is clear, right? Right. That's what I can say direction of armature flux. So guys, please try to see this. This figure. This figure. It's very important. So please try to understand. Initially, GNA and MNA they are under no load conditions. They are coincident. See, this is the but vertical line. Whatever I taken. This is only GNA. This is only your MNA under no load condition. Okay. So once again, though you know, I'll show once again. Please. This GNA and MNA, they are under no load conditions, they are coinciding with each other. They are coinciding with each other. So if you observe clearly here, I'm using for making you to understand, I'm using main flux. I'm just using yellow color for main flux. I'm just using blue color for armature flux. And I'm using red color for resultant flux. Please try to have that differentiation so that you'll be having some clarity. So initially under no load condition, yes, GNA and MNA, they are coinciding with each other. Now guys, if you observe clearly under load condition, MNA shifts from GNA by an angle of theta. So please, if you see under no load condition, GNA and MNA, GNA and MNA, they are coinciding with each other. And if you observe clearly, initially under see if you take this figure, try to observe the direction of armature flux. This is what I can direction of armature flux. No, that means indirectly it is armature flux is downwards, right? So please try to see direction of armature flux downwards. So downwards. So please this downward arrow mark only I am just showing here. So before shifting of brushes, I'm just under no load. Okay, GN and MN they are coincident. That is leave it. Okay, just forget about the topic. GN and MN they are coincident with each other under no load condition. That is okay. Now let us discuss under loaded condition. Because of armature current, you'll get armature flux. So that armature flux will be downwards here. This is what I can say direction of your armature flux under a load condition without shifting of brushes. I'm saying without shifting of brushes. Okay, let me write here. Without shifting of brushes. Without shifting of brushes. Without shifting of. Without shifting, simply I can say without shifting brushes. Okay, guys. Now, and what about main flux? I think from left to right, right? From left to right. If you want, I'll show you once again. Please, left right. This yellow color indicates direction of main flux, which is from left to right. Okay, which is from left to right. So if you observe clearly, what is the angle between your main flux and armature flux here? What is the angle between your yellow color flux lines and blue color flux lines here? 90 degrees, no? 90 degrees. Okay. Yes, that only I'm just showing here. Please, yes. This is what I'm saying. Angle between pi m and pi a 90 degrees here. Okay, guys. This pi m is what I can say pi a without shifting of brushes. And if you observe clearly, vector sum of this pi a and pi m. To this pi m, let me add pi a, or to this pi a, let me add pi m. You will get resultant flux, I can say pi r. If you observe clearly, this resultant flux is this red color indicates direction of your resultant flux. So this red color is nothing but this one only. I think you are able to see. Let me use laser point here. Excuse me. Yeah, this one. Okay, this is nothing but the direction of resultant flux. This only I just showed here. Okay, guys, please try to have some clarity. Main flux, this yellow color flux lines, this one. Okay, and armature flux downwards, this blue color fluxes. Okay, and what about resultant flux? I can say this red color. So these things only I just showed here clearly. Pi m, pi a, vector sum of pi m and pi a gives you pi r. Yes, this pi is without shifting brushes. Now, because of resonant flux becoming like this, so I told you are having cross magnetic effect, shifting, sparking of the brushes. To overcome that, what we are doing here, so whenever Mn is shifting by an angle theta from GNA, just shift your brushes also along Mna. So if you shift brushes along Mna, this figure indicates shifting of brushes along Mna. So after shifting brushes along MNA, if you observe clearly, guys, this direction of your armature flux, I can say this pi A will be in the direction of MNA. Do you agree or not? In the direction of MNA only, your pi A is there. Okay. So this pi MNA means this one. I'm just showing this MNA. So along MNA only, your pi A is there. Please let me show armature flux now. Once again, let me use same color, blue color only. But after shifting brushes, I can say pi A will be in the direction of your MNA. So those are having doubts, please try to see this figure. MNA will be in the direction of your pi A will be in the direction of your MNA, magnetic neutral axis. Yes, that's why this is what I can say magnetic neutral axis. I'm just showing pi A along MNA. Okay, guys. Now let me show this pi A is nothing but this pi is nothing but, so after shifting of brushes along let me write here pi A is nothing but shifting brushes along MNA. That means after shifting brushes along MNA, this is what I can say pi A becomes here, and this pi A is having two components, one along y-axis, let me show like this, one along x-axis, let me show like this. Okay, guys. Okay, so please try to understand clearly this component, let me use laser pointer. This component is making how much angle with respect to your pi m? It is making 90 degrees with your pi m. I already told you, if there is a 90 degrees angle between main flux and some flux, you are going to have cross magnetizing effect. That's the reason why this component of armature flux can be taken as cross magnetizing component of armature flux, because it is making 90 degrees with your pi m. So let me indicate that pi AC. Pi AC means what? Cross magnetizing component of armature flux, because it is making 90 degrees with your pi m. And what about this component? I told you pi is having two components, right? One along y-axis, one along x-axis. So if you observe clearly, this component is making let me use laser pointer. Yes, this component is making 180 degrees with your pi m. Do you agree or not? This is what I can say pi m. This is what I can say a component of your armature flux. It is making 180 degrees with your pi m. We already know if there is 180 degrees angle between the main flux and some flux, you are going to have a demagnetizing effect. That's the reason why this component of armature flux can be taken as demagnetizing component of armature flux. So I'm just naming it as pi AD. Okay, guys. Pi AD means, I think there is no need to write. Pi AD means demagnetizing component of armature flux. Pi AC means cross magnetizing component of armature flux. Okay, guys. So I told you MNA previously is shifting from GN by angle of theta, no? So if you take this one reference, once again this is nothing but theta angle. Here once again you'll be getting theta angle here. Okay. So guys, for if you take this triangle, so let me use laser pointer. If you take this right angle triangle, okay, apply sine theta formula. Sine theta equal to opposite side means for this angle, opposite means this side. This is nothing but this one. I can say pi AD. By hypotenuse, I can say pi A. Yes, I can say pi A here. So from this pi AD equals to pi A sine theta I'll get. Similarly, apply cos theta formula. Cos theta equals to adjacent side by hypotenuse. For this triangle, adjacent side means I can say pi AC. Yes, pi AC by hypotenuse means I can say pi A. From this pi AC equals to pi A cos theta. So guys, please try to understand. I got pi AD formula pi A sin theta, and I got pi AC formula pi A cos theta. So where theta means what? Shifting of MNA from GNA. Okay. So if you observe clearly, as theta increases, I mean, tell me when theta will increase. Whenever load increases, your theta will increase. That means as load increases, generally you know that theta increases. And generally as load increases, we know, because armature reaction we are having a CME and cross magnetic effect and demagnetizing effect here. So to reduce CME only, we are going shifting brushes along MNA. Now my question here is, if you increase, I mean, if you as the theta angle is increasing, your sine theta is increasing, no? Okay, that means pi AD is increasing here. That means DM effect, already we are having demagnetization effect is there because of armature reaction. Everybody knows that. So in addition to that demagnetization effect, we are having a additional demagnetization effect is coming here. So shifting brushes along MNA. So if because of this process, if you observe clearly, already we know because armature reaction we were having a demagnetic effect. Okay, and we were having cross magnetic effect also. So that I already explained in the previous session. Now what I'm asking is, to reduce cross magnetic effect, we are shifting brushes along MNA. So here problem is, so because as the angle as the load increases, as theta increases, your pi sin theta increases, your pi AD increases, means pi AD increases means what is the meaning for that? Demagnetizing effect increases. That means already you are having a demagnetizing effect is there because of armature reaction. In addition to that, some more DME is you are getting. Additional DM effect is coming here. Okay. But see, what about CME? Let us see. You see, pi AC equals to pi A cos theta. As theta increases, you know, cos theta will be reduces. Cos no, as theta increases, cos theta will be reduces. That means pi AC will be reduces. That means, try to understand, as theta increases, here pi AC reduces means cross magnetism effect will be reducing. As theta increases, pi S reduces, that is CME reducing. You know, whenever cross magnetism effect reducing, I told you commutation will be improved, sparking at the brushes will be reduced. All those things are very, I mean, important things only. But the problem is, CM is reducing, okay, but additionally your pi AD is increasing. No, that's a problem here. So addition, but pi AD increases, that is DME increases additionally. There is a problem here. Okay, so tell me then, what is the solution for that? Suppose if we were following this technique, shifting brush along MNA to reduce CME, we come to know that because of shifting brush along MNA, no doubt CME will reduce, but additionally demagnetization effect is coming. So now please tell me, if you know this one, so you should take remedy, you should take a solution for that. You should give solution for reducing this additional DM effect. How can you reduce the additional DM effect? So let us see. For reducing DME, okay, what you have to do means, so DME means what? Reduction of flux. That means you have to compensate that. So for that, what you have to do? So you have to place some extra turns should be placed, which can, I mean, you have to place some extra turns so that I can reduce this GME. Okay. So my question here is, how can you find extra turns means? So extra turns can be placed, which can be found by knowing demagnetizing ampere turns per pole. See guys, ATD per pole means what? ATD per pole means demagnetizing ampere turns per pole. If you know how much demagnetization effect you are getting under each pole because of shifting brush along MNA, so by knowing that ATD per pole value, you can place some extra turns. Okay, because I'll give you relation, you will be having some clarity. Let us see. How many extra turns you have to place means NSS extra into ISS. I take an example, shunt machine. So NSS extra into ISS equals to ATD per pole. That means NSS extra means number of extra turns should be placed on each pole. So let me write clearly here. This NSS extra means number of extra turns to be added on each pole. That is very important. On each pole, that is very important point here. Okay. Here NS extra means, I'm just, please try to understand, this is what I can say on each pole. On each pole, how many extra turns you have to place means, if you know how much demagnetization effect you are getting under each pole, if you know ATD per pole, if you know demagnetizing ampere turns per pole, so NSH extra into ISH equals to ATD per pole. Try to understand guys. Here A ampere turns means indirectly ampere turns means NI, nothing but MMF only. Here also I'm writing MMF only. Try to understand, okay? A ampere turns are number of turns into current, everything same only. If you know demagnetizing ampere turns per pole, NSH extra into ISH equals to ATD per pole. From this NSH extra equals to ATD per pole by ISH. So this many extra turns I have to place on each pole to reduce the DME which you are getting additionally because of shifting brushes along MNA. Okay. This for shunt machine. Suppose if you take for series machine, similarly for series generator, NSC extra means series turns extra turns, series extra turns into in place of ISH. I can write ISC, or you can write IA, because you know in series machine series field current and armature can everything same only, you know. Yes, I can write here NSC extra into ISC, or I can say IA is equals to ATD per pole. So from this, guys, if you want NSC extra, so what about this formula? ATD per pole divided by what? I can say ISC or IA. This only I wrote here. Okay. So NSC extra is equals to ATD per pole by IA, or I can say ISC. So here my question is, yes, you can calculate how many extra turns I have to place on each pole to reduce this DME which you are getting additionally because of shifting brush along MNA. That is okay. But this can be find out. NS extra in case short machine, in case of series machine, NS extra can be find out if you know ATD per pole only. So let me give formula for demagnetizing ampere turns per pole. Okay. So yes, for that, for giving that ADD per pole formula and ATC per pole also, I'll give simultaneously. I'll be giving here demagnetizing ampere turns per pole. I'll give formula, and cross magnetizing ampere turns per pole also I'll be giving formula here. Okay, so very important for GATE or PSC as well as for IS examination also. This important formula ATD per pole, ATC per pole. Okay, let us see. See guys, now same figure only. So here MN is shifted from GNA by an angle of theta. Okay. So if it is theta, what of this angle is theta now? So let me take one more reference MNA. So I had taken one more reference. See this generally, let me laser point raise. Yes. You know this MNA is shifted by an angle of theta from GNA by an angle of theta under load condition because of armature reaction. That is okay. And if it is theta, this angle also becomes theta. If it is minus MNA, please let me take one more reference axis making theta angle here. Yes, this theta means once again this one also becomes theta. Okay, theta, 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 theta. Total I am taking here 4 theta. Okay, so I'll tell you what is the reason why I have taken like this. So please tell me, guys. I'll ask a simple question. Please try to understand. Okay, so first of all, tell me your main flux lines. We already know. I already used for main flux. I'm using yellow color. So main flux is always going from north pole to south pole. Let me show here once again here. So please let me show main flux lines here. Yes, main flux lines. Let me use yellow color for that, and let me show you main flux like this. Okay, right. Here my question to you, very simple question I'm asking. Please try to understand clearly. In this 4 theta region, I can say in this region, and this region, this region. In this 4 theta region, observe guys clearly. So, what is the direction of your armature flux and main flux? Whether they are opposing, aiding, or I can say they are cross magnetizing. I mean to say that angle is 180 degrees, 0 degrees, or 90 degrees. I'm asking very simple question. I'm asking. Please try to understand clearly. So for that, you have to apply right hand thumb rule. So see in this theta, in this 2 theta region, first of all I'll apply. Next I'll go for theta in this 2 theta region I'll apply. Okay. So guys, if you apply right hand thumb rule, so here cross means direction of armature current entering, and cross indicates direction of current entering into the board. So please, in right hand thumb rule, your thumb should be into the laptop, or I can say into the board. Is it okay for you? Please let me show into the board. If you show into the board, so what about direction of armature flux? I think if you apply properly right hand thumb rule, thumb should be into the board. Cross means into the, in this region, your thumb you have to show thumb into the board, and remaining wrapper fingers shows direction of your armature flux. It will be clockwise. Please check once. You people should get direction of armature flux should be in a clockwise direction. Please try to check once again. Okay, if you're having doubt, please check once again. Okay, so tell me now, in this 2 theta region, your armature flux is opposing main flux or aiding main flux? So you have to see this flux amount. Please don't, some people are confusing. Sir, main flux I said yellow color, no, they are going from left to right, sir. And armature flux they are seeing here. So let me use laser point here. I'll tell you where people are doing wrong. Yes, they'll be seeing main flux means yellow color. Yes, it is from left to right, okay. And instead of seeing armature flux in this magnetic region, they are seeing here. Don't see this one, okay, because here we don't have any main flux, right? We don't have any main flux here. So we have to see the direction of armature flux where main flux is there. So in this region main flux is there. Yes, try to see your blue color arrow marks, they are opposing your main flux or aiding main flux. See, don't see direction of pi a means this one. Left right, don't see left right, okay? You have to see right to left because you have to see the magnetic region. Don't see here because here the main flux is not there. So please guys, in this region your pi m and pi a they are opposing. That means in this theta, since pi a is opposing your pi m, you are having demagnetizing effect. Okay guys, in addition to this 2 theta region, yes, to be frank, in this 2 theta region also you'll get a dm effect only. If you want, you can check once again, please. In right hand thumb rule, once again, your thumb into the direction of armature current which is out of the board. So thumb should be out of the board, or I can say out of the laptop screen. So direction of armature flux will be anti-clockwise direction. It will be like this. Anti-clockwise means it will be like this. Okay. Once again, so whether pi is opposing your pi m or aiding pi m means you have to see this one. Don't see this one. Okay, let me use laser pointer. So you have to see this portion, not this portion, because here there is no main flux here. Please, if you see magnetic region, this is what I can say magnetic region where main flux is there. Your pi m is from left to right, your pi a is from right to left. Yes, it is opposing. So guys, tell me, now in this theta, for in this 4 theta region, out of 360, I can say out of 360, in 4 theta region, you are having a demagnetizing effect. So please let me write formula for ATD per pole means demagnetizing ampere per pole means I can write formula like this: 4 theta by 360. Out of 360, I can say that for in the 4 theta region, you are having demagnetizing effect. Let us see in remaining region what will happen, we'll see. Okay, anyway, and let me write formula for this ADD per pole. So ampere, please, I'm just directly giving formula. I'm just directly giving formula for ATD per pole. So you can remember formula like this. Say ATD per pole means what? Ampere turns. Ampere means I can say IA. Ampere means, you know, general IA, no? IA. You should not forget, you should take IA by A. A means what here? Number of parallel paths. So ampere means IA by A. By A means what? Number of parallel paths. So ampere means IA by A, ampere turns. So tell me what is the relation between turns and number of conductors? Z by 2. You know already, number of turns equals to Z by 2 only, no? Okay. So I can write here, ampere means for ampere I'm writing IA by A. A means number of parallel paths, where A equal to P, number of poles for lap winding, A equal to 2 for wave winding, that already we know in the construction of DC machine. Okay, ampere turns means Z by 2. To be frank here, Z means I can write armature conductors by 2. Okay, if you want you can write, no doubt, nothing wrong here. ZA by 2. That ZA means what? Armature conductors by 2. Okay guys, ZA by 2. Ampere turns means I wrote ZA by 2. Ampere turns per pole. Per pole means I can write here by P. That's it. So like this, we can write simply formula for ATD per pole. 4 theta by 360 mean IA by A. Ampere means IA by A into turns means ZA by 2. Per pole means I can write P here. Okay, this like this you can remember formula directly. There is only derivation, all the things. Okay guys. Now here number of parallel paths, A equal to P for lap winding, A equal to 2 for wave winding. Okay. Now, so let us see here. Don't confuse guys. Some people are confusing here. Theta means is it electrical or mechanical? So guys, please try to understand. Theta means electrical only. It's not mechanical. It's not mechanical, because if you observe clearly in our example, how many number of poles I taken? Excuse me. How many number of poles I taken here? Tell me. In our example, I taken 2 poles, right? You know relation actually electrical angle equals to P by 2 into mechanical angle. Okay, since P equal to 2 in our example, electrical angle and mechanical angle will be equal in our example. But be careful in examination, instead of giving a number of poles to, if he has given whatever poles, okay, you have to convert a mechanical angle to electrical angle by this relation. P by theta electrical equals to P by 2 mechanical angle. So please guys, in this formula, theta is in electrical. But in our question, electrical angle, mechanical angle, both are equal because I had taken P equals 2 poles. For 2 poles, P electrical angle equals to mechanical angle. Okay. But generally, electrical angle will be, theta will be in electrical. Okay. That's it. Now guys, and what about except this 4 theta region, what about the remaining region? Remaining region means I can show you like this. Yeah. Remaining region means I can say this one, in this portion, and in this portion, in this region. Please tell me what about you are having, which type of effect you are having in this region. So please try to understand. So if you want to know the effect of, effect of armature reaction in this region, in this region and in this region, let me laser pointer. Yes, in this region, and in this region. Already we know in this 2 theta, 4 theta region, you are having DM effect. And I'm just explaining about the remaining region. Example, this portion and this portion. So tell me guys, in this portion you are having a GMEA, ME effect or CMEA. So very simple. For that, once again you have to apply right hand thumb rule. So here I got armature current cross. So direction of, in right hand thumb rule, your thumb indicates direction of armature current which is entering into the board. So direction of armature flux will be clockwise. So it will be like this. Okay. So tell me, almost all, what is the angle between your main flux and armature flux here? I'm asking you angle between your blue color flux and this yellow color flux. So you are having 90 degrees, right? Yes or no? 90 degrees, yes or no? That means in this region you are having a cross magnetizing effect. I told you already. If angle is between main flux and armature flux is 90 degrees, you are going to have a cross magnetizing effect in that region. Okay, guys. Now what about in this region also? I got direction of armature current dot. I'm getting dot means out of the board. For thumb indicates direction of armature current which is out of the board. So your wrapped fingers indicate direction of armature flux is in anti-clockwise direction. So please let me show an anti-clockwise direction means it will be like this. So once again, yes, it is making how much angle? Not only here I can see in this total except let me show you. Yes. Okay. So yeah, wait. This one, this one is why actually I erased it. Let me show you this main flux. Okay, and let me show armature flux once again in this region. It is out of the board, no? Out of the board means it will be anti-clockwise direction. So anti-clockwise direction, yes, like this. Okay, so observe clearly once again in this region also. What is the angle between armature flux and main flux here? I am asking angle between a blue color flux lines and yellow color flux is almost 90 degrees, right? 90 degrees. That means once again you are having a cross magnetizing effect. So I can write formula for 80 degrees per pole. 80 degrees per pole means what? Cross magnetizing ampere turns per pole equals to formula. So out of 360, let me for in this 4 theta region you are having DM effect. So in the remaining portion you are having cross magnetic effect only. So let me write here 360 minus 4 theta by 360, and remaining I told you how you have to remember formula. I already told you. Demagnetizing, cross magnetizing ampere turns per pole means ampere means I can write simply IA by A ampere. Turns means ZA by 2. Turns per pole means I can write P here. Okay, that's it. So this is about formula for ATC per pole and ATD per pole. So guys, if you know ATD per pole formula, I already told you. So I can place after calculating ATD per pole, simply ATD per pole by ISH gives you NSS extra. I have to place on each pole to compensate DM effect which you are getting additionally because of shifting brushes along a MNA. So very important formula. So please try to understand this formula. Okay. Next. So, but the thing is what I am saying here. So, for what is the problem in this method? So, for every change in load, theta will be changes. So, for every change in theta angle, you have to shift brushes along MNA. Okay, which I mean is it's not, I mean for every change in theta you have to shift brushes along MNA. So I mean that becomes complicated. Okay, so that's what I'm saying. This method is what I can say it's outdated method. In olden days they were using shifting brushes along MNA to improve commutation, or I can say to reduce CME, to reduce CME is outdated. Okay, nowadays interpoles, interpoles can also be called as compoles. I'll tell you that interpoles or compoles are used to improve commutation, or to reduce sparking of the brushes, or to reduce cross magnetic effect. Okay, so in olden days they were shifting brushes along MNA, but I told you shifting of brushes for every change in load, for every change in delta, for every change in theta angle it is difficult. So it is outdated method. Nowadays I can say I'll be using we will be using interpoles, or I can say compoles. Okay, we'll be discussing interpoles, not now. So before that, actually I need to explain here waveforms. After explaining the waveforms, I'll be taking a commutation. So what is a successful commutation, what is good commutation, what is under commutation, so why you're getting sparking of the brushes because of cross magnetic effect, that we'll see. After explaining that portion, I think we can go for interpoles and compensating winding. I told you already, compensating winding is used to reduce the DM effect. Interpoles are used to reduce CM effect. Okay, we'll see that. So but in this session, in addition to shifting of brushes along MNA, okay, let me see waveforms here. Let me see waveforms. What is the shape of main flux? What is the shape of I can see armature flux? What is the shape of armature MMF? What is the shape of resultant flux? All those things. Okay, right. So this is what I can say, shifting pressure along a minute to reduce CME. Okay. Now see guys, for explaining waveforms, so please let me show you this figure once again. Let me show you this figure once again. So if you observe clearly, let me take this entire thing as a machine, DC machine. First of all, I'm just starting my journey from this. So I'm just assuming that we are here. Okay. So I already told you, my entire discussion is regarding generator point of I'm discussing here. Generator means in our example it's a clockwise direction. So in clockwise direction, first of all, let me start my journey from this point. I'm here. First of all, brushes. Then in the clockwise direction, after brushes, you'll be getting a north pole, and north pole also you'll getting a leading pole tip. Next, I'll get a trailing pole tip. Next, I'll get once again. Brushes will get. GNA will get. Next, you'll get south pole. In south pole also you'll get leading pole tip. Next, once again you get trailing pole tip. We'll come back to this portion. Like this only, I just shown in this figure. Please try to see. For explaining this waveforms, I taken first of all Q axis. I can say GNA. This is nothing but whatever I taken reference in our figure, in that figure. So this portion, this is nothing but GNA. Already we explained our axis which is passing between poles can be called as Q axis, right? Yes, I'm here. Okay. So after this, in a clockwise direction, we should go for north pole, leading pole tip. So please let me show you north pole leading pole tip. Next, north pole trailing pole tip. Once again, after that, you'll be having Q axis. Next, south pole leading pole tip, south pole trailing pole tip. We'll come back to normal position. Okay, guys. So like this, in the direction of generator, I had taken like this. Okay, I had taken. Okay. So first of all, let me explain main flux. Then we'll go for armature flux, result flux, all those things. First of all, you tell me. We know formula of flux is equals to mmf by reluctance. Yes or no? Reluctance proportional to what I can say, air gap. This formula we already know. Okay. Flux equals to mmf by reluctance, where reluctance proportional to air gap. So please tell me, guys. I'm asking a simple question. And before that, I think I had taken under north pole. How many conductors I had taken here? If you want, I will show you once again, please. Yes, under north pole, you are having one. Okay, 1, 2, 3, 4, 5. Okay, 5 conductors I had taken. And south pole also taken 1, 2, 3, 4, 5. Okay, that means I'm having 5 conductors under north pole, 5 conductors under south pole. Okay, so under north pole direction of armature current I got a cross. So that one I just showed here. See, cross 1, 2, 3, 4, 5 I taken. Here also under south pole you are getting a direction of EMF dot 1, 2, 3, 4, 5 I get. Okay, I'm getting. Okay. Now guys, please tell me, I'm just going to explain how we are getting this main flux. How we are getting this main flux. So for that I need this formula, flux equals mm by reluctance. So please tell me along GNA, along brush axis, tell me guys, air gap is maximum or minimum? Please try to see clearly and tell me. I'm asking this region. Along Q means this region only. I mean air gap is maximum, minimum. Air gap is maximum. And what about along D axis air gap minimum? So I am saying here air gap is minimum. Here it is maximum. Yes or no? Okay. That means try to understand, guys. If you are along the q axis means air gap is more. Okay. If you are going away from q axis, that means we are coming from q axis to this d axis, air gap will be slowly reducing. Let me use laser pointer here. So please try to understand, along q more air gap. If you are going away from q axis, that means we are going towards d axis, means air gap will be slowly reducing. And suppose if somebody is coming towards q axis, example, if you are, I'm here d axis, if you are coming from d axis to q axis, you already know that at q axis air gap is more. If you are coming from d axis to q axis, means air gap will be increasing. Okay, so please try to understand the small 2 points. I mean very simple 2 points, because for every time there is no need to show this figure. At a q axis air gap more, going away from q axis air gap is reducing, so coming towards q axis air gap is increasing. Okay, simple points. And what about under poles? Under poles you are having uniform air gap, or what I'm saying, I'm using chamfered poles or non-chamfered poles. I think we know chamfered poles means, guys. Chamfered poles means, let us see. In synchronous machine, those who are having doubts, please try to refer. In synchronous machine, I think we explained the flux distribution air gap for chamfered poles and non-chamfered poles. For chamfered poles and non-chamfered poles. So, I mean, non-chamfered poles means air gap will be uniform under pole shoe. See, I think you're having a uniform air gap here. Here same air gap, here same. Okay, you're having a same air gap under pole shoe. These poles can be called as, I can say, non-chamfered poles. What about chamfered poles? Chamfered poles means, I think I explained in a synchronous machine. Anyway, let us see here. If you see chamfered poles means we'll be having like this. Example, if you take this portion, okay, here non-chamfered means you'll be having like this. Air gap, if you observe clearly, under pole shoe, if you see observe, air gap is uniform. I think you are, it is very clearly visible, right? So how much air gap is the same air gap under your pole shoe? For, I can say, non-chamfered poles. For non-chamfered poles. Okay, guys. But for chamfered poles, if you observe clearly, if you observe clearly, so along pole center, okay. So what I can say, along pole center, tell me air gap is less or more? Air gap here it is less. Air gap less. And if you are going towards pole ends like this or like this, if you are going towards pole ends, air gap is increasing. Okay, air gap is increasing. This is what I can say, chamfered poles. Okay, these type of poles can be called as chamfered poles. So I think I already told you guys, for chamfered poles, distribution of flux in air gap will be sinusoidal, whereas for non-chamfered poles, distribution of flux in air gap will be trapezoidal, or I can say flat topped waveform, which we already discussed in synchronous machine. Please try to refer that. Otherwise, let us see, in our DC machine, we won't use chamfered poles, we'll be using non-chamfered poles. That means, I told you already, if I use chamfered poles, you are going to have a sine wave. So, and if you use a non-chamfered poles, you are going to have a flat topped, or I can say flat topped, or I can say trapezoidal. That is DC machine, you have to prefer flat topped trapezoidal than sine wave. So whereas in case of AC machine, generally we need sine wave, because we don't want any harmonics. Therefore, in alternator, if you observe clearly, we were using in silent pole machine, we were using chamfered poles for making a flux waveform sinusoidal. But here DC machine, so we need flat top waveform or trapezoidal waveform, not sine waveform, because here harmonics will be there. Flat top waveform means when compared to the sine wave, harmonics will be there. There is no doubt in that. But here, harmonics is not matter in case of DC machine. Okay, if harmonics are there also, there is no problem in DC machine. Always you should give importance for, magnitude of your induced EMF. Okay, so magnitude of induced EMF will be more, average value of induced EMF will be more for flat top waveform than sine wave. That's why in a DC machine will be preferring a flat top waveform, trapezoidal waveform only. That's why we are using what here. I will be using a non-chamfered poles, not chamfered poles. We'll be using non-chamfered poles. Air gap will be uniform under pole shoe. Okay, so please try to remember that. And let me explain those waveforms. First of all, I'm just starting my journey from this point. So please try to remember those 2 points which I told. What are those 2 points? Along Q axis, air gap is more. If you are going away from Q axis, means air gap is reducing. If you are coming towards if you are coming towards Q axis, means air gap is increasing. Those points you have to remember, guys. Now let us explain how you are getting shape of armature, main flux, armature flux, resonant flux, all those things. I told you along Q axis, I can say brush axis. I'm explaining first of all, main flux. Let me use here laser pointer here. Along Q axis, I told you air gap is maximum. Whenever air gap is maximum, reluctance will be maximum, flux will be minimum. So let me take almost of 0. Okay. And guys, if you are going away from air gap, that means if you are going away from a Q axis, from Q axis, if you are coming towards D axis, I told you, if you are going away from brush axis, if you are going away from Q axis, means air gap will be reducing. Okay, those who are having doubts, you can refer this figure. Every time there is no need to show this figure. If you are going away from this Q axis, means if you are coming towards this D axis, means air gap here it is more. Slowly air gap is reducing here. So please try to understand. Yes, air gap is reducing here from here to this point. If air gap is reducing, reluctance will be reducing, flux will be increasing. That's why your main flux will be increasing in this manner. Okay. And what about under pole shoe? I told you we are using non-chamfered poles. Air gap will be uniform here, almost all uniform air gap here. So if air gap is uniform, air gap remains constant, means your flux remains constant here. That's why you are getting this flat top. Okay. And from this trailing pole tip of your north pole, if you are going towards Q axis, I told you if you are coming towards Q axis, means air gap will be increasing. If you want, you can refer that figure. So if you are coming towards Q axis, means air gap will be increasing. Air gap increasing means reluctance increasing, means flux will be reducing. Yes, flux is reducing like this. At the Q axis, air gap is more, so flux will be less. I took it as 0. Once again, from this Q axis, if you are going towards south pole, so I told you if you are going away from Q axis, means air gap is reducing. Yes, reluctance will be reducing, flux will be increasing. Flux increasing in negative fashion like this. And under this north pole, if you see pole shoe, air gap is uniform, so flux remains constant. Okay, so you are getting flat top portion here. From this south pole, trailing pole tip, we are going towards the Q axis. Air gap is once again, I told you, if you are going towards Q axis, means air gap will be increasing. So reluctance will be increasing, flux will be reducing. Yes, flux is reducing. At Q axis, air gap is more, so flux becomes 0. So please guys tell me what is the shape of main flux we are getting here. So please, what is the shape of main flux you are getting? I think you know, but once again, please try to understand. What is the shape of main flux you are getting here? Flat top, or I can say trapezoidal waveform. Let me show here. This is what I can say main flux. Main flux. You can say pi m. What is the shape for this one? Flat topped or trapezoidal waveform. Okay, guys. Next. Now, before explaining armature flux, okay, let me explain armature MMF, then I'll go for armature flux. Okay, guys. So, for explaining armature MMF, in this figure, armature MMF means this one only, this green color waveform. But if I draw directly here, you'll be having some confusion. That's why I just separate explain here. Okay. So I think I taken under North Pole. How many number of connectors I taken? 1, 2, 3, 4, 5. Yes, I taken one dash. I mean, sorry, 1, 2, 3, 4, 5 connectors I taken. After North Pole, you'll be having once again QX will be here. Let me show QX here. And on the South Pole, I told you how many number of connectors we are having here. 1, 2, 3, 4, 5. Yes, 1 dash, 2 dash, 3 dash, 4 dash, 5 dash. That means, guys, 1 dash is a coil. 2 dash is a coil. 3 dash is a coil. 4 dash is a coil. 5 dash is a coil. Now let us show you how armature MMF waveform will look like. So for that, please tell me what is the shape, what is the formula for armature flux? Armature flux formula equals to armature MMF divided by reluctance. Where reluctance proportion once again air gap. Okay, so please try to see. Let us see for explaining this armature MMF waveform. So tell me, armature MMF means what? Number of turns, number of armature turns into armature control. Yes. So please, first of all, for explaining for drawing armature MMF, let me take 1 dash coil, 2 dash coil, 3 dash coil, 4 dash coil, 5 dash coil. For all these 5 coils, let me draw armature MMF, and if I add all those things, that becomes total armature MMF. So let me explain first of all armature armature MMF of 1 dash coil. 1 dash means this black or vertical is nothing but simple only for reference. When I just drawn all those things for reference point of view, I just drawn all those things. Okay, and if you want 1 dash, guys, it will start from 1, it will go up to 1 dash. Okay, and once it will take a negative portion like this. Okay, this is what I can say armature MMF of 1 dash coil. Similarly, if you take a 2, if you want 2 dash armature MMF, it will start from 2, it will go up to 2 dash, and it will take, and your waveform will be like this, 2 dash. Okay, similarly, what of 3 dash, it will start from 3, it will go up to 3 dash. Okay, and yes, this becomes armature MMF of T3 dash. Similarly, you can draw from 4 to 4 dash, from 5 to 5 dash. This becomes armature MMF of 1 dash coil, 2 dash coil, 3 dash coil, 4 dash coil, 5 dash coil. So if you want total armature MMF, very simple. So we'll simply adding only. If you want, what about this value? If you want this value means, so tell me, guys, in this portion, this is what I guess a negative portion here. Here also negative portion. See, I had taken this white color means this is a reference line only. Reference line. So I got here negative portion for 1 dash. If you see armature MMF, we are getting negative portion here. Here also negative portion for 2 dash. For 3 dash also negative portion. 4 dash also negative portion here. 5 dash also negative portion here. So that means you are getting 5 negatives. 5 negatives means you are getting more negative. This much negative portion. That's why I just got this portion. Okay, similarly, if you see this one also negative will be more negative up to this. Okay, and let me explain in this region, guys, here positive negative cancel, and let me take here negative 3 negatives. That means it is previously is 5 negatives, now it's 3 negatives. No, let me draw one up to this only, like this, simply adding all those things. Okay, and here also it get 3 negatives. And what about in this region, guys? In this region, positive negative. So 1 positive 1 negative will cancel. Here 1 negative already, already 1 positive, 1 positive, here 2 positives, 2 negatives will cancel. You'll be getting only 1 negative. That's why you're getting in this region only this much portion you're getting. So simply, I hope you understood easily. Simply adding all those things, and if you try to take all those things by adding simply all those things here in this region, you'll be getting all positives. You're getting 5 positives, will be more positive here this portion. So I think it's very simple. By adding all those things you can draw. And let me take reference points here. Let me join all those points. This becomes armature MMF waveform. Okay, guys, so I think there is no need to explain. Simply adding all those things only, and just take reference points and just join all those things. You are going to have armature MMF waveform. So observe, guys, clearly what of this axis, north pole south pole means this polar axis can be taken as d axis. No, yes, this is the d axis. Here also I can say d axis. Observe, guys, clearly, if you draw total armature MMF waveform, you draw, okay, this is the maximum along which axis? Q axis. If you observe clearly, it is maximum along Q axis. No, maximum along Q axis. Okay, and minimum along which axis I can say dx. Along dx it is 0, along d it is 0, along q it is maximum. So please let me note on those points here. Armature mmf, armature mmf is maximum along q axis, and it is minimum along dx, because it is armature mmf is minimum, armature mmf is minimum along d axis. Okay, okay, right. Now here my question for you. So guys, tell me, armature flux equals to armature mmf by reluctance, where reluctance equals to air gap. That means armature flux depends on air gap as well as an armature mmf. Tell me, it is mainly armature flux is mainly affected by what? Armature mmf or air gap? So please try to understand, armature flux depends on, no doubt it depends on armature mmf and armature mmf and air gap, but mainly depends, that is very important, but mainly depends on, air gap. That you should not forget. Okay, so it is depending on armature mmf and air gap, but mainly depends on air gap. Okay, armature mmf and air gap, but mainly depends on air gap. So please try to remember these points. And this armature mmf, whatever I got, what is the shape of this armature mmf I am getting here? Triangular. Okay, triangular waveform, see, try to see this waveform. It's a triangle, right? So this triangle waveform I'm just showing here. Along q I showed more value here, along d it's a less, along d it is a less. Okay, along q it is a more, along q it is a more. So if you join all those things, you are going to have armature mmf waveform. So I just used a green color for that. So let me write here, armature mmf. What is the shape we are getting here? Triangular. Okay, now let us draw armature flux. I told you armature flux equals to what? Armature mmf by reluctance. No, reluctance equals to air gap. So please guys tell me, where air gap is constant? I think you already know where air gap is constant. Under pole shoe, whenever under pole shoe air gap is constant, simply armature flux follows what I can say, armature mmf. Yes or no? That means, observe guys clearly, in this region, and in this region, if you observe clearly, in this region and in this region, observe clearly. If you want me to draw armature flux, since air gap is constant, simply it follows armature mmf. Like in this region, armature mmf is following in a linear fashion like this. So let me use laser point here. Yes, in this portion or wherever under pole air gap is constant, so there armature mmf is green color waveform. If you see, this is nothing but linear fashion. In the same fashion, your armature flux also, it will be varying like this. Okay, and under this south pole pole shoe also, air gap is constant, simply it follows armature mmf. Yes, here under in this region, the armature mmf will be this green color one. So armature flux, this blue color will be, it is varying in the same fashion just like armature mmf. Okay, now what about remaining portion except this pole shoe region? In remaining portions, I told you that this armature flux mainly depends on what? Air gap. Okay, now tell me, you know that along q axis air gap is more or less? Air gap is more. No, air gap more means armature flux will be less. Yes or no? Yes, less. But don't make it zero. Why? Though air gap is max along q axis, okay, at the same time along q axis armature mmf also there. No, see this much portion. Understand? Along q axis, no doubt air gap is more. Okay, don't make armature flux to zero, because along q axis, yes, air gap is more, at the same time armature mmf also more. No, this much. See, therefore it depends on armature flux, depends on armature mmf also. So yes, definitely because of more air gap we can show less value, but don't show pi a value to zero. You have to show some value. Yes, that's the reason along qx, if you see this blue color waveform, okay, I'm not making it zero value, I'm just showing some value here. If you want, I'll show you. Let me use some color. Let me use some black here. Yes, what I guess some small amount of value I'm just showing. Don't show pi a to 0, okay? And similarly, if you see along qx, once again here also, don't show 0, some value is there here. Once again along q, don't show 0, some value is there here. I'm just drawing your result, some armature flux is there. Don't show along q axis pi a, that means blue color waveform, to 0. Okay, your blue color waveform will not become 0 along q axis. Is it okay for you? Next, now let us see how it is varying from q axis if you are coming towards north pole leading pole tip. Everybody knows that from q axis if you are coming towards leading pole tip of north pole, air gap is reducing or increasing. Along q, air gap is more. If you are coming towards north pole leading pole tip, means that means you are going away from q axis, means air gap is reducing. Air gap reducing means what will happen to your armature flux will be increasing. Yes, simply that's why I'm just showing increasing like this, okay? And yes, this portion already explained. And in this polar region, in this pole shoe region, since air gap is constant, simply it follows armature mmf, okay? And from this trailing pole tip of north pole, if you are coming towards q axis, it's a common sense that if you are going towards q axis, means air gap is increasing, so flux will be reducing in this manner. Reducing, it is reducing, but I told you at a q axis it is not 0, some value is there, because though air gap is maximum along q axis, still armature mmf is there. That's why don't make it to 0, okay? And from this q axis, if you are going towards leading pole tip of south pole, if you are going away from q axis, means air gap is reducing, so flux is increasing like this, is increasing like this, okay? And I think I already explained this portion. Under this pole shoe region, since air gap is constant, it follows simply just like armature mmf. It's a linear fashion like this. So once again, from the trailing pole tip of south pole, if you are going towards q axis, means towards q axis, your air gap is increasing. Yes, flux will be reducing. Yes, reducing, but don't make it 0 along q axis. Though air gap is maximum, but armature mmf is there. That's why don't show 0. Okay. So guys, if you observe clearly, what is the shape of armature flux you are getting here? So if you draw the shape of armature flux, see, if suppose if width of the width of this blue color figure is less, means you are going to have like this. You are going to have like this. You are going to have shape like this. Okay. What is the shape? I can write this one. It's just like a saddle peak, no? It's just like a saddle peak. Okay. Because since width is more here, I'm just getting like this. I'm just getting like this. But to be frank, you are getting figure like this. Okay. So guys, what is the shape of armature flux? This one I can say armature flux, so nothing but pi a. Okay, what is the shape of this one? Please, it's a saddle peak waveform, Okay guys, now let me draw a resultant flux. Very simple. Pi r is equals to vector sum of pi m and pi a. So pi r bar equals to, I can say, pi m bar plus pi a bar. So simply add all those things. Just if you want regular waveform, simply you have to add yellow color waveform and blue color waveform. If you add yellow color waveform plus blue color waveform, you are going to have red color waveform. See guys, at this point, let me use laser pointer so you'll be having some clarity. Yes. At this point, your yellow color waveform is main flux is 0, but armature flux is there, some value is there. So your pi r equal to pi a, yes, it is starting from pi a only here along the q, pi r equal to pi a. Therefore, this is this one. And what about along MNA? Along MNA, I told you magnetically neutral axis. I told you already, guys. The magnetic neutral axis means what? The axis along which no induced EMF in a conductor. No induced EMF in a conductor. That means if you observe clearly, if you see a resonant flux waveform also, with resonant flux waveform also, if you see, so you are along MNA, if you see value of your pi m and value of your pi, it will be same. Okay, in our figure we are getting like this, but generally it will be same. If you want, I will show you here. This value along MNA, this value is same when compared to this. Okay, if you draw figure neatly, yes, definitely you'll get same value only. It's same only, guys. Okay, along MNA, I can say pi m and pi a will be equal. So it will be value because what? 0. So I told you already, along MNA, the axis, what is the definition for MNA? The axis along which there is no induced EMF. Okay, that means resultant flux also will be equal to 0. So please let me show wherever I can say pi, wherever MNA is there let me show your resultant flux waveform, resultant flux value 0 here, 0, okay, 0 here, 0 here, and here MNA, yes, here it is 0, here it is MNA, here it is 0. Okay guys, please, wherever MNA is there please make pi r equal to result flux equals to 0. And what about if you see this at this portion, your pi a is this much, your pi m is this much, so more value of pi m is there, so result value will be at positive side only. Yes, this is the value. And what about at this point, your pi a is 0 but pi m is there, your pi r equal to pi m, so this is the point. And what about under trailing pole tip? And trailing pole tip, this is what I can say pi a value. And what about pi m value? This much. So if we add both things, we'll be getting more pi r value. See, so from here to here, this much value, more value. Okay, more value. And if you see along qx once again, so pi m 0 but pi r is there, so your pi r equal to pi a only. And along mn, I told you it is 0. And at leading pole tip, your pi a is this much and pi m is this much. So more negative, more pi m value, more pi m is more dominant here, so pi r will be negative side only. At this point, pi a is 0 but pi m is there, so pi r equal to pi m. And a trailing pole tip of south pole, yes, pi a is this much and pi m is this much, so your total value will be this much. Okay, more value. So, and once again at this q axis, yes, I told you your pi m is 0 but pi a is there, so that's why pi r equals to pi a only. And what about this portion at mn? I told you it is 0. Okay, yeah. So guys, if you observe clearly, excuse me, yeah, so if you observe clearly, what is the shape of resultant flux you are getting here? Shape of resultant flux, see this one, this radical, if you observe clearly, what is the shape of your resultant flux you are getting here? So let me write here, this can be called as air gap flux, or I can say resultant flux, resultant flux, resultant flux. So what is the shape of this one? Peaky waveform, peaky waveform, peaky waveform. Okay guys, peaky waveform. So I'm not saying any new things. Already, whichever we already discussed, the same things what I'm explaining here. If you want, I'll show you. See, in the from this waveforms, if you observe clearly, the resultant flux waveform, you just try to observe clearly. Under trailing pole tip, we are getting more value. Yes, sir, that means on trailing pole tip, we are having a ME effect, DM effect, ME effect only. See, more value of flux, no. And leading pole tip, your resultant flux value is this much only, this much. That means you are having a DM effect, ME effect, DM effect. So let me change the color because your reticle is not clearly visible here. It's a ME effect, and here it is a DME. So because here less value, here it is more value. And here also, see on south pole leading pole tip, your resultant flux, if you see this much value, only less value, I can say DMA effect. And if it is south pole trailing pole tip, we will be getting whatever resultant value, resultant flux value, this much more value, they are getting a ME effect. Guys, you please should understand. This we already indicated in the, in our first figure, which we used for explaining armature reaction. If you want, I'll show you once again. See, north pole, yes, let me show you here. If you take north pole, trailing pole tip, ME effect. North pole leading pole tip, okay, DM effect. South pole leading pole tip, DM effect. South pole trailing pole tip, ME effect. So same things only I am writing here. Okay, yes or no? I'm not saying new things. Trailing pole tip means ME. Leading pole means DME. But generally, for here, for drawing approximately, I just showed a trailing pole tip, more flux I just shown here, more flux I just shown here. And at a leading pole tip, I just shown 0 flux here. But to be frank, not 0. Some value of flux will be there here in this leading pole tip. The small value only, if you see, I can, here, this is the value. This value of small amount of flux, okay. So practically some small amount of flux will be there, but there I showed simply 0 flux, okay. So here, if you see here leading pole tip, some small amount of flux will be there. Leading pole tip, small amount of flux will be there, okay. But here I just showed almost all 0 flux at leading pole tip, But to be frank, yes, some flux is there, okay. So guys, the same things only, whatever we explained, I'm just once again explaining by using waveforms only. Okay. So guys, you try to remember only one thing here in this entire discussion. So in GATE examination, they won't ask you to draw waveforms, all those things. Please try to remember the shape of your flux waveforms. Okay. I mean to say, what is the shape of main flux? Your answer is flat top or trapezoidal. What is the shape of armature mmf? Your answer is triangular. What is the shape of armature flux? Your answer is saddle peak waveform. What is the shape of air gap flux, or I can say residual flux? Your answer is peaky waveform. That's it. Okay. And try to understand one point. If you see these waveforms along q axis, if you see resonant flux waveform, do you think that resonant flux is zero at along q axis? No, some value is try to show here. Is some value is there here, some small amount of flux is there along the q axis. If you see resonant flux waveform, red color waveform along q axis, it is not zero. Some value is there here. See, some small amount of value is there here. Here also some small amount of value is there here. So because of this only, you are getting some sparking in the brushes, which we'll discuss later. So please try to have some keen observation. So guys, this is about your waveforms. Okay. And in the next video, I think we'll be discussing compensating winding. I told you compensating winding is used to reduce the DM effect, that I'll tell you. And after explaining this one, we'll go for commutation process, because after explaining computation, here I explain what is good computation, what is the poor computation, all those things. Then I'll be going for using interpose, I can say compose. I told you in olden days they were using shifting brushes along M-minute to reduce the cross magnetic effect, to reduce sparking the brushes. Now, but that was outdated method. Nowadays we are using interpose or compose. That I explained. But before that, I should see commutation definition, commutation topic. And before that, let me take here how can you reduce the demagnetizing effect by using compensating winding. Then I'll come to interpose. Okay, guys. So that's it for this session. So please try to follow clearly. And the next video, I'll be taking compensating winding. Okay. If it is possible, I'll take commutation topic also. Otherwise, I'll take commutation topic separately. Okay, guys. Okay. Thank you.